Well, so first, obviously, thanks for the honor of being able to speak with you today. I have really had a wonderful day touring around and talking to people and getting a sense of what's going on here at Purdue. And I have to say that there's really some impressive work going on here. I think that you should all really be proud of the institution and the faculty and what's going on. Today, I'm going to talk about, so I thought for a while about what sort of talk I want to put together, but I decided to talk about work that really is pretty close to my heart, intelligent machines that learn to augment people. And maybe just a little kind of explanation / ad for Johns Hopkins. So there's really two entities that I've highlighted up here. One is the Laboratory for Computational Sensing and Robotics, which we founded about 10 years ago, which is the home of robotics research at Hopkins. It is about between 20 and 30 faculty from around campus that are involved in robotics, over 100 graduate students, and very broad effort in robotics, but with deep roots in medicine in particular, taking advantage of the natural strength of Johns Hopkins. And then I'm actually the founding director of a new center, the Malone Center for Engineering and Healthcare, which you can think of really as kind of the complement of the world of robotics, saying, how can we broadly bring technology into healthcare delivery with the goal of making a more efficient, a safer, and a more consistent system of healthcare. And so we actually are interested in, obviously, technology spaces like robotics, but we also are very interested in taking techniques from AI, from systems modeling and optimization, human factors, industrial engineering, to really understand how do you look at healthcare as a system and how do you improve it. And you'll see in my talk, I kind of flip back and forth between those two hats, one being coming more from the traditional robotics and vision world, and the other thinking much more coming from applications driven by medicine. And in fact, in that vein, let me just also put out an ad. I have a lab that's really fairly broadly involved in computer vision and robotics in both healthcare and non-healthcare applications. And we're always looking for great grad students and postdocs. So if you are interested in doing the sort of work that I talk about, I would love to hear from you. We would love to see if we could get you to Hopkins. So as I said today, I was kind of going back and forth about what of all the different type of work that we do I want to talk about. And I kind of like sometimes starting a little bit historical, namely back with a talk I gave in about 2000 at ICRA, the Robotics Automation Conference, where I was actually at that time doing work primarily in visual servoing. And we were starting to build these tools and this programming system that made it possible to start to think about taking everyday implements like this and building a robot that would be able to manipulate them and do sort of high precision vision-based control of those tools. But the gist of the talk was to say we're getting better and better at some of these very fine-grained level manipulation components that we're hand architecting, but we're missing some of the big picture components. So we're missing the ability to recognize objects. We're missing the ability to model how humans interact with each other and with those objects during a task. And so what I said is, at the time, my son Lucas, who was about 5, I said, he comes down to the workshop and he's my second set of hands. And I know I'm going to lose him in about 13 years when he goes off to college. So the field has 13 years to figure out how to solve these problems. So I have a workshop assistant by the time he goes to college. Well, we kind of missed that mark. He's actually got his first job these days. And so I did lose my personal workshop assistant. But the neat thing is that we really are, I think, as many of us recognize in robotics, entering a new era of what I'll call intelligent systems. And it's really intelligent systems driven by a convergence of any number of technology advances. So I mentioned object recognition, the fact that we now are starting to see perceptual capabilities that in some narrow cases can rival human capabilities means we can really start to think about building perception-based systems. Automated driving systems are kind of pushing the notion of how do you model dynamic environments and how do you actually interact with drivers. I'm going to talk a lot about medicine. Robots have been out now in surgery for getting close to 20 years now, and we're starting to gain a lot of experience of how those systems can be useful. And Ready Robotics, which Juan mentioned in the intro, is really focused on small and medium enterprises, where what we'd like to do is to build a tool that is as easy to use as your iPhone, but as capable as any smart system you can imagine, that a small business owner who's doing, say, metal manufacturing can use as really a Swiss Army tool in their workshop, but have someone who's just a normal factory floor worker develop and interact with that tool. So, when I think of what I was talking about back in 2000, I see, a lot of opportunity and capability there. And in fact, in our lab, we started to see the beginnings of those workshop assistants. But what I'd like to talk about today is kind of the complement of that, which is that as we get more and more smart systems in the hands of users, as more farmers are driving GPS-enabled tractors with all sorts of sensing, and people are driving cars with all the sensing capability, basically testing cars and getting road miles. And as we get more and more procedures under the belt of a robot in the operating room, what we're really getting is we're getting a new lens on how humans perform complex physiocognitive tasks. So tasks that really involve both physical manipulation and cognitive ability. And what that means is we can, for the first time, start to use that data to study both how people perform those tasks, as well as how might we start to think about developing systems that can complement human capability and augment it, and really make people better and more productive at what they do. And although I've kind of called out these four areas, it's worth noting that there is innumerable areas where this sort of notion of what I'll think of as apprenticeship training, learning from somebody who knows how to do the task already, is incredibly valuable. If you look at many of the major crafts like being an electrician, being a mechanical engineer, being a plumber, being a metal worker, these are areas where even though there's a lot of talk about loss of manufacturing jobs in the United States, in fact there's tremendous underemployment at this point in these areas. And furthermore, the workforce in these areas, so here's, for example, computer-controlled machine operators, it's looking at how many are over 55 and how many are over 45. Nearly half the workers in that area are over 45 years old, and something like a third are over 55 years old. So there's actually this tremendous kind of skilled worker gap that's growing, and it's actually not being backfilled right now by the kind of ambient forces of economics. We through Ready Robotics, we talk to a lot of small manufacturers, and their biggest problem right now is how do we enhance productivity when we can't hire the people we need to hire to actually fill the jobs that we have. And so this really kind of sets the stage for what I've been thinking about for many years now, and plan to continue to think about, which is, if we're now seeing these smart systems, we're seeing these new forms of data, we're seeing a really interesting space of needs and opportunities, how do we actually get robotics on the path of thinking about developing these sorts of skilled assistant systems? And what are the technical challenges, and how can we overcome them? And I like to say, this is a problem that you can go almost any direction with. I think this picture to me captures it. It's not just about observing behavior, but it's really interaction at many levels. It's observing behavior, it's advice giving, it's giving feedback, it's cognitive training and understanding. And so you can imagine a very rich space of research that is really involved just around this developing and kind of nurturing research directions in these types of assistants. So in the rest of this talk, what I'll be doing is really giving you a little bit of a synopsis of work that we've been doing over the past few years along two complementary themes, but themes that really, as I say, complement each other. I think they, as we'll see towards the end, they come together. One is more on the coming from the robotic side and more motivated by these manufacturing tasks, which is how do you build an assistant that is easy to use, is task aware, and can interact and assist a human. It's a system we call CoStar. It's an open software system. You can go and download it now, which provides perception-enabled interaction capability and programmability of a variety of robot systems. And on the other side, coming from surgery, learning to understand how people perform skilled tasks in a high-value setting like surgery. So understanding skill deficits, and ultimately how we can do coaching and instruction. So without further ado, what I'm going to do is, in fact, start on the side of understanding skill and skill deficits as a way of kind of motivating, well, what is the structure of task performance when we start to look at the data that we get? And then I'll end with a little bit on where we've been taking that with the CoStar system. So this is the skill side of things is a project we call the Language of Surgery. It was coined a while back. It actually started because we first thought of it when we started to work with Da Vinci robots, and we realized we're getting these signals coming out that are time series, and we wanted to structure them. And so I went to my colleagues in speech and language and said, how do you guys deal with speech data? And after a few discussions, we realized there were a lot of analogies to be made, and so we started to say, well, can we take ideas from speech and language, initially at least, and bring them into surgery? It's, again, an interesting area to work in for a couple of reasons. Just to kind of motivate some of the opportunities and the needs, I like to point out that the current method of training in surgery and medicine broadly was, in fact, developed or really imported by, at Johns Hopkins University by William Halsted. He was traveling in Germany, and he noticed that they had this sort of graded apprenticeship system in their hospitals. And at the time in the United States, there was no organized method of teaching medicine. And so when he compared the two, he said, we've got to bring this system back to the States and start to create an organized curriculum around medicine. He actually brought it back. It turns out it was William Welch, one of his co-founders at Johns Hopkins, who then promulgated it through first the hospital and then ultimately through other medical schools in the United States. But it is fundamentally an apprenticeship system. It's fundamentally, for surgery in particular, you come in, they call it see one, do one, teach one. People like to think that's surgery, but it's not the case. You see a surgery, you do a surgery, and you teach it. It's you see one type of surgery for a while, and over time you get familiar with it. You're given responsibility in a graded fashion in different parts of the procedure, and then ultimately, as you become expert, the mentor fades from view, and now become the expert, and you teach it to the next person down the line. So that's see one, do one, teach one. Now, one of the things you should know about surgery is that it's not like there is a final exam in surgery. They don't wheel a patient in and say, okay, this is your final exam. Depending on how you do, you'll get your surgery certificate. No, it's you basically go through surgical training. When you finish training, you go off and you be a surgeon. So obviously there's a certain variability in people's natural ability and the amount of time they get in the OR. There's any number of reasons you see variability in people's skill as they emerge from surgery. And that persists through their career too, depending on how active they are in surgery and how broad a set of surgeries they perform. And this has real impacts. There's a study by Birkmeyer recently where they looked at the impact of skill on outcomes. And the way they did this is they did video review of, in this case, bariatric surgeries. And the whole idea was to say, look, why don't we give a surgeon a grade of 1 to 5 based on what we perceive their skill level is and the surgery that's being performed. And then they went back and they correlated that skill level with patient outcomes. And so you can see the results are pretty stark. If you look between the top quartile and the bottom quartile, you see roughly twice the readmission rate, about twice the reoperation rate, almost 3 times complication rate, and in fact it's not 3 times, it's 5 times the mortality rate between the top quartile of skilled surgeon and the bottom quartile of surgeons. So there's really a reason that we would like to enhance the quality of training and the uniformity of training and really address whatever deficits is defining the difference between the top and the bottom quartile. And this has real public health impact. This is really saving lives and saving dollars in medicine. As I already said, the starting point for our investigation was the observation that in surgery, really before driving and many other areas, you were starting to see the opportunity to get data at scale to study how people perform surgery. And that was because with the advent of the Da Vinci system, you had interposed a computer between a surgeon and the patient. And all the information going in and out of the patient was going through that computer. And so you could capture it. So you could get stereo endoscopy from inside the patient, all the video that the surgeon used to guide their decisions and actions. And you could capture all of the hand movements that were being transmitted into the patient as well. So you had a complete record of what the surgeon did and what they saw during that surgery. And furthermore, if you look at it today, there are actually, the growth pattern of intuitive surgical is such that they will most likely hit about 1 million procedures this year. So if you could, in fact, capture all of the data coming out of the back of every Da Vinci in the world right now, you would actually have 1 million procedures that you could start to study to say, well, what actually is common about surgery and different procedures, what's different about surgery. You could do studies like the Berkmeyer study and start to say, well, what differentiates a good surgery from a bad surgery? Now, just to kind of give you a sense of what this feels like, this is a video I've used for a while, and some of you may have seen it, but it's kind of a fun game. The goal here is for you to tell me who's a good surgeon and who's a bad surgeon. And I'm just going to play the video. What we've done is we've synchronized them a little bit, so you can't use speed. You have to use technique. But don't stress out. I don't think it's going to take you too long to figure this out. All right, so they're off and running. Person on the right seems to be ahead of the game. Well, person or left, your left is ahead. Person on the right caught up. I'm kind of thinking you already know. So the person on the left is somebody who is, in fact, a very skilled surgeon. He was a beta tester for the Da Vinci system. Person on the right is it's actually a resident who has had experience with surgery. They just haven't used the robot before, and so they're getting familiar really with how to use it. Out of curiosity, does anybody know what differentiates why the person on the right is one of the reasons why the person on the right is having so much difficulty? Yeah.
Are they left-handed?
Nope, they're right-handed, both right-handed. No, it's not perception. It's, sorry, what were you saying?
The configuration of the hand. Like the
Yeah. You got it. If you look at ergonomically what they're doing, they're grabbing the needle in the wrong way. And if they grab the needle the way they're grabbing kind of at the end, they have very poor needle control. The expert is grabbing it orthogonally, and that's what gives you good needle control. So if I were teaching them surgery, that's the first thing I would say is, hey, if you just hold the needle differently, you'll probably start to do better. And that's what coaching is about in surgery. If you take the data on what those surgeons are doing, that's what it looks like. And I think you can see that you can perceptually easily tell the difference between good and bad. And if you look at the data, you can see that there's a pretty obvious signature that says, here's something that's really organized, here's something that looks much less organized. And that's really the signal that we can start to use to understand what are the signatures of skilled versus unskilled. So one way that we looked at this, for example, is you can take those data sets, and you can see the color coding. You can think of those as kind of primitive phonemes. We call them surgemes sometimes. Kind of like words are formed from basic sound units. Well, these tasks are formed from basic movement units. So we can plot how they use the basic movement units. And this is what an expert looks like. You can see they're very efficient. They're very linear. Basically the loop backs are running the different suture lines. This is what a real novice looks like. You can see they're just all over the place. They do things in different orders. They go back, they go forth, they drop the needle, they start over again. In fact, a couple of these gestures you see that an expert never even uses, but the novice uses them many times. So from that, we could then take these, think of this as a transition matrix. We could map that down to a two-dimensional space. This is actually using multidimensional scaling. And if you do that, you can actually start to plot where novices, intermediates, and expert trainees, or expert surgeons in this case, lie. And you can see there actually is this kind of interesting space of skill that evolves, where you start out as a novice, and then you kind of move along. And the other thing you notice is experts are pretty tightly clustered. And that's something that we see generically as we look across this work, is that novices are all over the place. Every novice is bad in their own unique way. But experts become very good at what they do. And a lot of becoming good is becoming very consistent and uniform in how you do things. And so this was the idea behind the language of surgery, is to say, hey, we've got this data. We're starting to develop techniques that we can use to use this data to have a lens on how people are performing tasks. And what we've done then over the subsequent now about 10 years is kind of push that further and further and further till we say, can we start to really build, if you will, an AI-enabled surgical assistant, both for training and execution of surgical tasks. And so what I'd like to do is to kind of give you just a few kind of highlight snippets of how we think about that nowadays. I'm going to really give credit to Anand Malpani. He's now a research scientist at Hopkins. He finished his PhD with us, I guess, about a year and a half ago, where he really focused on this question of how could we develop, if you will, an AI-enabled or data-enabled coaching system for surgery. And he broke it down into this set of activities. And it's kind of useful to think of these activities and kind of how we would actually accomplish all of them. And I'm not going to say I'm not going to show you a full coaching system yet, but I think I can show you kind of how far we've gotten. And you can see a lot of these activities are kind of, almost a closed loop. So the trainee does something, they get evaluated, maybe based on that evaluation they get some critique, and that then go back and do some more. They get monitored over time to see how they're doing, and if they're not progressing in a certain area, maybe a certain type of practice is recommended that they do. And so a lot of what we're doing is we're kind of filling in these feedback loops with computational algorithms that allow us to say, hey, we can look at what you're doing, but we can also productively or we can intervene to produce a better learning curve or better performance. So let me start a little bit with this monitoring and evaluating. You've already seen a picture of that where I said, look, I can take this data and I can differentiate a novice from an expert. But I have to say the data I showed you is a little bit artificial. It was a benchtop task. There was a lot of manual intervention that it took to kind of get to the point that we could do those analytics. And so a lot of what we've been pushing toward is to say, can we do this meaningfully in live surgery, and can we do it meaningfully in a broad set of tasks? So just to kind of give you a sense of how we think about this, a lot about what we think about is that there is some sort of an innate structure to tasks. And really what we want to do is we want to capture that innate structure. Now in that older work I showed you, we hand structured that. We literally sat down with the surgeon and said, okay, tell us what you think the basic units of surgery are. But as in many things these days, as we get more and more data, we'd really like to let that representation emerge from data. So this is some work that Nargis Amidi, a former PhD student, did a few years ago where she started to look at this and said, well, how can we capture this kind of innate structure of the trajectories that show up in surgery? And she invented this kind of neat encoding where what we do is we take the tool trajectories, we build a Frenet frame on those trajectories, so we build a local coordinate system defined by the trajectory itself. And then relative to that local coordinate system, over a short time frame, we can code what is the shape of the trajectory that comes out. Are they moving sharply right? Are they moving sharply left? Are they accelerating quickly? Are they slowing down? Are they going backwards? And you can think of each of those as now being a discrete letter. And so what really comes out the back end of this encoding is a set of strings. And so now as you see more and more and more performances, what you can do is you can essentially do a bag of words style approach. You can start to say, are there common repeated substrings, for example, in the set of all expert trials? Are there common repeated substrings in the space of all novice trials? And those repeated substrings are trajectory snippets. They're really those surgenes. And we can build a dictionary. And now we can say, given a new trial, which dictionary actually best explains the performance of this person on that task. And we can do that to discriminate different types of gestures they're performing, or we can actually make the dictionaries about their level of expertise and find essentially distinguishing strings or words or features, if you will, that define expertise versus novice. So we've actually deployed this in a real surgical setting. This is actually sinus surgery. So the procedure called septoplasty is what we're looking at. It's what's called an index procedure in surgery, meaning that it's something that every surgeon in otolaryngology has to do as part of their surgical training. So it's kind of this bottleneck where everybody goes through it. So it means it's a good place to build this lens, because we're going to see everybody who's training. And the procedure is actually an open procedure. So what we did is we added some sensors to the tools that they use so we can actually just get the tool trajectories. And kind of mimicking what I showed you before, if I look at a novice doing septoplasty and I look at an expert doing septoplasty, you can see again there's this pretty clear difference between an organized and efficient expert who's basically raising this flap of skin. That's what they're doing, the septal flap elevation part of the procedure, using this tool. So they basically work their way under the skin and raise it as they go around. And a novice who is clearly, or a beginning surgeon, I should say, who's clearly not yet familiar with the procedure, just not as efficient. They're still getting the job done. This is also an interesting procedure for us to do this in because as you can see, it's down inside the nose. The mentor can't actually see what the trainee is doing. So they can only kind of intuit from what they're saying and what they say they see, what they might or might not be doing wrong. So one of the things we actually did early on is we had a monitor sitting in the OR just so we could monitor our data collection system and see what was going on. And they actually complained when we took that away because for the first time we were plotting tool trajectories and they could actually see what the tool movement looked like of the novice. And their wetware was already starting to learn the difference between what they were doing and what the novice was doing just by seeing the tool movement on the screen. So it's really a great opportunity for an intervention. Just to give you a sense of how well things worked. So we tried a number of different metrics that are out there. So the thing you might first think of is to say, well, why don't I just take the raw signal and look at velocities and accelerations and jerk and snap and whatever your favorite higher order moments of the signal are. Turns out those signal-based metrics really didn't work very well at all, particularly if you gave them a surgeon they hadn't seen before. So if you just trained and tested on the same data, you could actually get up to about 70, 75%. But as soon as they saw a novel surgeon, it didn't work well. We also did something like you saw at the beginning where we built a structuring mechanism, strokes, and we said, well, can I tell a level of skill just using stroke metrics? And again, if we train and test on the same people, it does well. As soon as we go to a novel surgeon, performance falls. This is a recurring theme that we see. The method I just described to you, DCC, gets actually about the highest performance, close to 90% ability to discriminate an attending surgeon from a trainee, which is pretty darn good. And in fact, what was unique about it was that it maintained its performance almost completely as we went to de novo surgeons. So we were actually able to take someone we'd never seen before and with about 90% probability tell if it was an expert or a novice. So that was really exciting for us. It's the first time we're in a live OR setting and we're actually able to tell, is this person an attending surgeon or a novice that's operating. What's also interesting is we could actually start to track people through time. Because it's an index procedure, people do it over and over and over again. And so you could actually see somebody starting out as a novice, as I kind of showed you before, and you could start to see their evolution toward expertise. So there really is this kind of skill trajectory that we're starting to see moving through space. And here's that display I mentioned in the OR that they started to like. So this was actually, I think, a very successful project. We ended up getting a follow-on R01 on it. So we're actually right now collecting data in 6 operating rooms, both within and outside of Hopkins. The goal is to get about another 500 procedures in place and to broaden the set of people that we're involved with so that we're getting really much more representative data. The objective then is to, in fact, by the end of the project, be able to provide analytics to trainees and mentors that would help them to improve the training in this particular type of surgery. So the next thing you'd like to be able to do, kind of following in this diagram I showed you before, we can monitor and evaluate. That's essentially what I've shown you. But that really is kind of like giving you a test score, right? So if it's like I do surgery and afterwards I say, okay, you got a C-. You'd be like, what? I got a C-. How do I don't want a C-. I want to get A's and B's or A's. Actually, if it's a surgeon, they want A+. So how do I get better? Well, the score doesn't give you any insight into that. And so there are 2 elements that we've looked at for starting to provide more directed feedback to improving surgery. So the first piece is to say, well, if I just give you an overall score, you have no idea what component of the surgery really was the part that you did well or poorly. So you really have to get more granular than that. And so you can think of surgery, though, as being, you can really break it down fairly hierarchically. So cholecystectomy, removing the gallbladder. There's a very well-defined procedure with a set of high-level steps, and each of those steps breaks down into sub-steps, and eventually they break down into basic surgical techniques. So one of the first things we needed to be able to do was to show that we could take the recording of a surgery, typically tool movement data plus perhaps video, and that we could parse and provide meaningful feedback if you can't find the right components. So we have looked at this in a number of domains. Again, I'll focus primarily on robotic surgery here. And just show maybe a bit of the work by Colin Lee, again, another grad student just now at Oculus, who really was interested in this question kind of generally of how do we take data on task performance, these, again, physico-cognitive tasks, and break them down using machine learning techniques, basically learn how to break them down into components. And so he really pioneered this notion of using spatiotemporal convolutional networks to do that. And so his general idea was to say, look, whether we're operating from video data or tool movement data, ultimately, what you first want to do is you want to be able to summarize kind of over a time period what's going on in a procedure. And then from that kind of summarization, think of those as just local temporal features, then put them together over time into whatever high-level phases at whatever granularity you want to parse them into. So this is actually a convolutional unit in space, and then this is a convolutional unit in time, typically. It's kind of neat to see what these convolutional networks learn, so I'll show you this. So this is actually a network that's been trained to do phase recognition in cholecystectomy. It's trying to identify one of 7 phases. But what I'll point out, this is the low-level feature maps that it's learned pretty much right at the image level. And you notice that we're plotting the maximum activation features. Notice that we never told it anything about surgical tools, but it actually has gotten pretty good at, I can run that again. It's actually gotten pretty good at recognizing the surgical tool when it goes in and out of view. And in fact, it's also picking up basically the primary targets of interest too. So kind of, if you think about it, the most natural latent variables, if I'm trying to decide where I'm what I'm doing right now, is to say, well, what tool is being used, where it is being used, and how it's moving. And so implicitly, it's essentially generated that representation, even though we never gave it a fine-grained representation of the tool. So to kind of cut what could be a longer story short, how well does this do? If you can work from 2 different data sources in this particular case. You can work straight from video. You can work from video plus some signals coming out of the robot about what tools are being used, or you can combine the 2. And this is on a data set that was published by the TU Munich a while back. And to make a long story short, if we use that spatial temporal network, we use a technique called dynamic time warping to go from a small dictionary of reference surgeries to match to the surgery that we're looking at to get the phase boundaries. We can get above 90% accuracy. And that 90% means if I ask you at any frame in the video what's going on, 90% of the time I will be correct in telling you what phase the surgeon is in. And in fact, we have some other data that shows if we give ourselves a little bit of a grace period at the beginning and the end of a phase, so give ourselves, say, about 30 to 45 seconds, that number goes up well over 95%. So most of the errors we're making are simply on the boundaries. When did this particular phase start and stop, which itself is a little bit ambiguous. I don't think I have the data in here, but I'll just say that one of the other kind of interesting sidelights of this was a pretty pristine data set. It was one hospital and one or a small number of surgeons operating. Colin actually went out and he created another data set he called EndoTube, where he just went onto YouTube and he downloaded every cholecystectomy video he could find. And he self-labeled it and said, well, okay, what happens when I turn this loose in the real world? So not surprisingly, it didn't do as well as 95%. but it didn't do bad. The results were kind of about 70 to 75% accuracy, which is remarkable when you think of the variety of image resolutions, technique variation. Some people suture instead of using clips. It's all over the place. And yet the methods were actually pretty reliable, being able to reliably segment out phase. So again, if you think of those million procedures, if we actually could seed these methods with a million procedures, I think we could actually get ourselves pretty close to being able to do pretty fine-grained phase analysis. I just threw this up as, we've also done some recurrent neural networks on some of the tool data, and we get kind of similar performance now at a very granular level, basically hand movements of around 90% reliability. So we really are kind of at the point that we could start to do that localization. So the last piece of this really would be to say, okay, I can assess you, I can do it at a granular level, but I still haven't told you what you did wrong. And you saw that in that first video, right? I told you what the diagnosis was. Well, can you somehow go from what's going on in the video to that diagnosis? So we've been starting to work in that direction. We're actually doing it not in robotic surgery, but we're doing it in cataract surgery right now. The way that we start thinking about it is really as an indexing problem, where again, if you think of a million surgeries, you've probably seen a lot of the sorts of deficiencies that are going to show up in the average performance. And so really what you'd like to do is to simply use that data in a reasonable way, namely capture, here's an example of a deficiency and in a particular phase, and here's what was suggested to correct it. And so the way we do that is we simply use the video itself as an indexing mechanism. So you can think of taking video and possibly kinematics, building a low-dimensional encoding of that video in kinematics, so we have some signature, if you will, using that to index into a database. In this case, we'll use nearest neighbor. Once we go to the database, we can say, okay, I've found, of all of the millions of procedures I've seen, I've now found the closest example to what you're doing right now. Do I have any sort of feedback that's attached to that particular video? It could be it's a good thing, and you say, hooray, you're doing great. Or it could be, you're holding the needle wrong, and I'd like to fix that. So we actually have the first version of this system up and running. I apologize if anybody's a little bit squeamish. This is one of the few slides that maybe people will go a little bit on. But the idea is to say, this is a query video. So this is, I said, from cataract. I'm going to basically just give to the system. It's got we've got about, I don't remember how many cataract videos at this point that have been broken up into components. Its job is to go and say, find the component video that's as close as possible to the one that I'm seeing here. And so it's really a straight up video lookup problem. And interestingly, it doesn't play. But so here we go. So on the left is a query video. And you can see it's the first penetration of the capsule to open it up. There's a video on the right, and I think you can see it's chosen something that obviously, a lot of the appearance is varied, but the fundamental actions that are taking place are about the same. So as I said, this is kind of a first result. We're trying to scale it up now, but it's definitely the approach that we've seen, fairly repeatably in other areas now is actually starting to work. And so we're hoping that we can build that into that recommendation system. So lastly, so I can give you some recommendation, but one of the things you'd like to be able to do is to demonstrate what to do. So in that needle driving problem, one of the things is I could tell them to hold the needle differently, but ultimately I'd like to show them how to hold the needle differently. So this is actually going back to Anand's work. So he looked at this when he was an intern at Intuitive Surgical. So we have access to their simulation system, and he was able to develop, you can see this little set of training wheels around the needle. So this is something you can turn on, which if you detect that somebody has some deficit in terms of how they're handling the needle, you can literally say, in simulation at least, hold the needle here. And all they have to do really is to match their hand to the needle, and then they can go off and do their task. So the kind of whole chain is to basically take the data, observe that they're skill deficient, observe where it is, identify this as the source, and now turn on a training wheel and say, here you go. Here's something that will help you get better. So we actually put a lot of this together in simulation to actually test it on a set of trainees. So this is done at Intuitive Surgical, again, by Anand. So it's a small trial where we took 32 trainees in surgery. We had a no-teaching group and a real-time teaching group, where the real-time teaching group was getting our stuff. And the idea was that they all got to practice 3 times. They both got kind of a front-end intro, here's what you should do. People who, the no-teaching group just practiced for a while and they got a final performance. The other group got first a practice run where the training wheels were turned on, a second practice run where we then just gave them feedback based on the metrics we computed, and a last training run where they could turn it on themselves if they wanted it or leave it off. So kind of a mixture of effects. And then the last performance, they had to go without the training wheels. And to make a long story short, we got exactly what you'd like to see. So blue is, means that the group that had the intervention, the training group, did better at whatever the metric is. You can see in particular we were focused on trying to correct deficits like that, holding the needle wrong. And so when we had the training wheels on, they all did significantly better than the experimental group. When we did our metrics, they continued to do better, just not quite as strongly as before. Interestingly, once we did that, you notice that their motion metrics and error metrics went up because they're a little less focused on doing exactly the right thing, so they sped up as well. User group, the effect persisted, and in the final group, you can see, in fact, we dominated in terms of deficit metrics and error metrics. So really almost exactly the effect that we'd like to see. Now, surprisingly, if we actively coach people, they do get better. So this is kind of hopefully gives you kind of a framing of saying, we really could start to use those million surgeries as a lens on, first, how do people learn? What does skill mean? And then how can we start to actually actively improve that learning curve as we go up? The starting point really is we were looking at this data, and we realized that we could use the same data we were getting for skill assessment to start to also do collaborative execution. So this is some work that Nicola Padoy did, now at Strasbourg, where we had our segmentation system running, and instead of assessing, what we did is we marked different phases of the procedure as manually performed or automatically performed. And automatically performed means that we just took the trajectories that we observed during the training phase, built some sort of average model, and then had the robot re-execute them. And so you can see it kind of gives you this nice handoff behavior where the person's doing the high-value piece of the procedure, and then as the system recognizes you finish that phase, it just switches over automatically, and it does the needle transition. And although this is, obviously it's kind of a nice just demo, it does actually make, it does actually improve the speed of suturing. So we could actually show that people were faster when they had this sort of auto mode, largely because they don't have to clutch over large movement spaces with the robot. But this was a really simple system. It was fun to see, but it really had no context whatsoever. It was purely by rote. But it did start to make us think about the question of how could we do better than that? Could we start to build more contextually aware systems so that I could take this system, which really only worked in that one benchtop setting, and start to move it out into the real world? And so you can kind of think of this as a question of saying, suturing, for example, is a basic skill in surgery. It's done over and over and over again. You need to be able to redeploy it in many contexts. So what is, if you will, an invariant representation for that task that you can carry across all the different instantiations of suturing? And that's really what's been dominating a lot of our robotics and learning work recently. How do we actually go from data to task representations that are robust and generalizable across context? So just briefly, the kind of general idea we've been following is to say that if we have demonstration data from tasks like in surgery, or you can imagine following somebody who's driving, or if you're running a manufacturing robot, seeing how a manufacturing robot is used, the task is implicit in the data that we're capturing. And so we'd really like to learn a representation from that data. but we want to do it in a space that, just like in the skill space, it's somewhat invariant to changes in how the world evolves or the different contexts you use it in. So this is Chris Paxton's PhD. Chris just finished last week, in fact, where we said, well, suppose we have this same sort of segmentation you saw before. Can we start to learn distributions over the trajectories that actually successfully perform the task, but do it in a space that's roughly invariant? So for example, if I learn in absolute trajectory space, that doesn't generalize. If I learn movements in a target object relative space, that possibly does generalize as long as I understand the right coordinate frame about that object. So Chris basically followed that approach. So you can think of it as basically building probabilistic models of successful trajectories for particular actions. And what he was able to show is he could first build that model, but he could actually build it into a motion planning system. And it's kind of neat. I kept this video in just because I kind of like to show how this works. Let's see if I can. So you can think of a task as being a multi-step task where you're trying to get trajectories that essentially satisfy the conditions of each stage of that task. So you can think of, can I now sample trajectories that satisfy whatever the predicates are? And so here is what the system then looks like, if I can get it to play. Very interestingly, it refuses to play. All right, well, it works this way then. Let me do this. This is called manually playing your video. So here it's just a training phase. So here's a little task where we're basically picking up a link, we're moving a link, we're orienting it, and then we're placing it. And so, as I said, the idea of this planning system is once we've done that several times, we have this distribution over trajectories that have been successful. If we move the objects around, we can basically recontextualize the coordinate frames for those actions and start to generate candidate movements. And then essentially what we do is we do importance sampling. So you can see that importance sampling process where we build samples, we evaluate them for being successful in simulation, and then we resample. And then eventually we find a small set of samples that are likely to be successful. We pick one and we execute it. Now you notice it didn't work so well there because we actually did it step by step by step. So the actual system basically does this jointly over all the actions. So it tries to imagine, if you will, a trajectory that would be successful in this particular context with high probability, and then goes ahead and chooses the action, and it carries it out. And to make a long story short, if you do this, you actually get good performance out of the system. And in fact, we've played with this, and as I said, we can actually, for a small assembly task like this, we can actually use the user data. We can build these models now that are contextualized to objects, and we can start to get some robustness to behavior. But there's one thing that we didn't like about this, and it's kind of the last piece of this, is to say we did a better job in some ways of now having a mechanism to generate open-loop trajectories, but what about closed-loop trajectories? And so, in fact, the core of Chris's thesis has been able to show that we can jointly learn both the actions themselves in a closed-loop fashion based on sensor signals using reinforcement learning. And on top of that, we can actually also learn a good predictor for the likelihood of success of a particular action in a particular context. And I'll just pop ahead to quickly say the basic idea. You can think of this kind of like the AlphaGo works that you've recently seen, where what we do is we train a neural network to look at a particular situation and predict the likelihood of success of a particular action. And then we can drop that into a planner that basically generates a sequence of actions at a high level actions that have a high probability of success. Each of those actions, options as we call them, is actually a recurrent, is a reinforcement learned controller that then controls the agent of interest. Chris actually went to Zoox, a car driving company where we could get a lot of data on car driving. And so he basically used that as a test case for this. And so you can imagine it's basically a system that's trying to learn how to drive a car through an intersection as efficiently as possible without running into other cars. And again, in the interest of time, I'll just run ahead and say, so this combination of learning kind of this high-level strategy piece plus reinforcement learning, the actions themselves, beat just about any other combination you can imagine. So you could try to program a manual policy. You could try to do a straight-up reinforcement learning approach. Or you can have this combination of learned low-level actions and this learned high-level action. And what's most interesting is, so in the case where there's no stopped car ahead, we basically get about the same performance in terms of constraint violations, collisions, and failures as a manual policy. We're actually a little bit better in terms of generating, well, about comparable in terms of generating reward. But as soon as you put a stopped car in the intersection, we actually do significantly better than the manual policy that was programmed. So the system actually learned to drive in unusual situations better than the pre-programmed manual policy, and definitely beat kind of a straight-up reinforcement learning approach. I'll just quickly say we're actually kind of continuing to push ahead on this, just to kind of bring this back to surgery. For many years, I said I didn't think that we could really do automation in surgery. I just didn't see that was going to be practically feasible. But I'm actually starting to see that might be possible. And so the last end of Chris's work was really to say, can we start to develop these planning systems but do it directly from video data, video observations of the procedure? Because that's what we get in surgery largely. And I'll just show you kind of a neat system he developed. This is actually a system that essentially we call robots with imagination. So we can do this in artificial, say, we actually have done this on our Da Vinci data, so going all the way back to where I started. We took hours of video of the Da Vinci. We ran it through this learning system to be able to start to predict images from a current image through an action. And so this is an image that you might give it as input. And then we had it predict goals based on certain actions that it took, like driving the needle or moving the needle away. So this is what the neural net predicted, literally the output of the neural net. And these are the real images that followed downstream in that video. And I think you can see that it's doing a pretty good job of predicting what the world is going to look like a few seconds hence based on current state and an action we give it. This is just another example of where we started, the predicted images. And the one thing you can see is it's not doing a good job of predicting the suture. So it's predicting the tools and the context, but not the suture line. So to kind of tie this back into what I was saying, we're really now starting to be at the point that we can not only mine that data to say, well, how is the surgeon doing? But these models are starting to be predictive models where we can, as a surgeon is performing, we can say, okay, you're in this state. I actually expect that you're going to take this action, and I expect that this is what's going to happen afterwards. And so I can either, if I want it to be autonomous, say, here's the action to take, or, what I think is more relevant, I can watch what you're doing and say, hey, are you doing something that is along the lines of what I would expect in this procedure? And if not, I can actually start to characterize that and either give you support and feedback or, again, use it in these systems to evaluate performance. And so maybe just to finish kind of where I started, I think it's a really exciting time in robotics because a lot of those problems that I, 15, 18 years ago, really didn't see how we were going to solve, we're actually starting to solve them. So we've literally taken that CoStar system I showed you before, we've dropped it on our surgical robot. We're starting to be able to perform kind of interesting manipulation actions on top of it. And we're starting to look at, can we literally, from observing surgeons at work, can we start to learn models of what performance looks like and what to expect in performance, both really for automation, but I think more importantly for assisting and making people better. And as I said, we're doing it in surgery, but I actually see this applying in many other areas as well. So with that, let me just briefly thank my clinical collaborators. So doing work like this, you don't sit in a lab and do it. You go to the hospital, and just had wonderful collaborators in many areas of surgery. I've had the luxury of working with a lot of really outstanding engineering collaborators as well, and of course many students and funding agencies that make it possible. And I'd also like to thank you for your kind attention, and thank you.